So we're in a course about knot theory, and that means that we eventually need to say what a knot is. And today's the day. So a knot in mathematics, in knot theory, is formally speaking the image of a smooth, simple, closed curve inside of space. And that is a big mouthful of language. First, the word smooth just means that I don't want to have any discontinuities or any kinks or sharp corners. I just want it to be, if you're thinking about calculus, sort of a differentiable curve. So it's just sort of a nice, unbroken, unkinked, unbent, just sort of curved around curve sitting inside of space. It's simple in the sense that we can't make this curve cross itself, right? It can't actually be, we can't have it literally self-intersect, right? We can't have a point in three-dimensional space which is on the curve twice. Every point that is on this curve is on it exactly once. And it's a closed curve. This is the sense of, plugging the endpoints into one another so that we get something that looks more like a loop. It doesn't have an ending, it doesn't have an end, it doesn't have a beginning, it just sort of is a continuous loop going around in space. If I have more than one of them, then taken together, we can say that they form a link. So if I have n of these knots all sort of residing in space in front of me, I could call the collection of those n things an n component link. We're not going to do much with links this semester, but you could imagine that, pretty much any of the topics that we discuss with knots, we can also soup them up a little bit and talk about n-component links. So here's the sense in which a knot can also be thought of as kind of like a function from the real line into three-dimensional space. The function just sort of tells me what point in three-dimensional space corresponds to that point on the real line. Right? It's just a way of kind of taking the whole real number line and sort of twisting it up with itself and joining the ends together in some way, and forming its image forms a knot inside of space. So we can study knots from an algebraic perspective as we will, but a lot of folks who study knots also study them from the perspective of geometry and topology, right? We can talk about things like, well, one of the most geometric ways to study knots might be to just sort of say, well, what shape does this knot make inside of space? Or sometimes what they'll do is say, what shape does space make if I remove this knot from it? Which is actually, topologically speaking, the most fruitful way to study a knot. Just take three-dimensional space and drill out a copy of this knot from it, and then ask what is the resulting geometry and topology of that space that remains around the knot. That is ultimately, when we look at topological invariant for knots next week, that's going to be where we get it from. Here's an example of a two-component link. Right? We have one red looping thing that kind of looks like a knot in and of itself. The black looping thing also looks like a knot in and of itself. And they also kind of are entangled with one another as well, as most interesting links would be. If I just have two knots that are sort of sitting side by side and not interacting, we could consider them a link, but that's not very interesting because they're not interacting with one another at all. So, as I was sort of hinting at in the introduction today, one of the things that makes knots challenging is that they do inhabit a three-dimensional space. And if we want to study knots, it's kind of difficult, it's challenging even for the most sort of spatially adept mathematicians to think three-dimensionally all the time about knots. We want to have something that we can set down on a page that we can use to study knots instead. And those somethings are called knot projections or knot diagrams. So one illustration of what a knot diagram actually is it's kind of what you would get if you were able to suspend a knot kind of in three-dimensional space as these artistic knots are being hung from a ceiling up here. And as the sun shines through them, it casts a two-dimensional shadow on the wall. And that shadow, if we could somehow on that shadow say like which of the strands is crossing over which strand at each one of these crossings, right, similar to how we do with braids, if we could include that information on that shadow, then we would have a pretty good representation in 2 dimensions of capturing some of the information about this knot. And so we would call this shadow, we would call it a knot projection. Projection is the kind of word we often use in analytic geometry when we think about the result of taking a higher dimensional object and kind of smushing it onto a lower dimensional hyperplane, as we're doing with this 3-dimensional knot, kind of casting a 2-dimensional shadow. Or if we also include that information about the overs and the undercrossings, then we get what we might call a knot diagram. And so it's a 2-dimensional visualization of a knot consisting of a set of unbroken curves that we're going to call arcs. So the arcs of a diagram are just the individual sort of two-dimensional curves that make up the diagram. And then a bunch of crossings at which exactly two arcs are meeting. So we're never going to have three arcs come together at the same point in a diagram. We're always going to try to tweak the diagram a little bit so that we can see exactly what's happening where only two arcs are coming together. And every time two arcs come together, we have to specifically say which one is crossing over, which one is crossing under. So in this little interactive here that you can find in our textbook section, we're looking at a knot that's called K32. Sometimes this is called the trefoil knot. It's one of the simplest knots. This is an example of a diagram of that knot having three crossings. If you look closely at this crossing over here by my mouse, this sort of east to west strand is going over the north to south strand. At this one, it's the northwest to southeast. It's going over the northeast to southwest. And at the third crossing, the northeast to southwest is passing over, and the other one is passing under. And so what we're looking at here, right, is a two-dimensional representation of a knot. But of course, there's many different two-dimensional representations of a knot, of the same knot, that we could look at, right? We can make different diagrams just by adjusting our perspective a little bit. For example, if I just sort of rotate this knot in space a little bit, I can create diagrams that are considerably more complicated than the one that we started with. Right? Here's another diagram of the very same knot, but instead of having three crossings, we've got 1, 2, 3, 4, 5, 6 crossings, right? And so if somebody comes up to you on the street, because I know this happens to me a lot, and hands you a diagram and asks me, what knot is this? That's not necessarily an easy question to answer, right? Because we might sort of, sit down and make this knot out of physical rope or wire or something, and then maybe we can manipulate it in space. Or if we have a nifty, three-dimensional interactive like this one, if we could just sort of take it and say, well, this looks complicated, but if I just rotate my head a little bit, I'll see that it's the same trefoil knot that we started with. Then that's pretty simple. But this turns out to be a challenging question in general. It's not just challenging intellectually for humans to think about. It also turns out to be really challenging for computers to think about. There are not any really good efficient algorithms that are out there for determining whether two diagrams represent the same knot. But we'll get a little bit more into those weeds as we talk further about this today. So the central question that we're trying to confront here is, to what extent can a diagram capture enough information to tell us what knot that we have and what properties that knot might enjoy? So where I want us to start with your teams today is to start with this trefoil knot, K32. Either construct a copy of it using rope or wire, or you can just use this virtual interactive. This was built with GeoGebra, if you're interested. Sketch a diagram that has three crossings, and then change your perspective so that you can find a diagram and sketch a diagram that has more than three crossings. So just come up with a couple of different diagrams and sketch them out for this same knot. You can use a virtual version or you can use a physical version, but just get at least two different diagrams down. And the name of the game today is going to be asking things like, well, what do all of these diagrams have in common by virtue of the fact that they all originated from the same knot? That is the big question of the day, and this is how we'll get started. All right, so far so good. Using the applet or using your physical string, you're able to come up with several different diagrams of the same knot that we're calling K32, called the trefoil, that have different numbers of crossings. And so this original diagram, which is seemingly probably the simplest diagram we could sketch, has only three crossings. But these diagrams over here, they represent the same knot, and yet they have different numbers of crossings. Here's an example with 6 crossings. It still represents the same knot because all we did to see it was just rotate that trefoil inside of three-dimensional space, and we're seeing more crossings. I really like this example too, because here's an example of a diagram of this same knot again that has 4 crossings. So just by rotating our perspective a little bit, we're able to add exactly 1 crossing to this diagram. So again, the big question of the day today is, can diagrams be a useful tool for us, given that the same knot can have so many different diagrams that represent it? All right, how can we possibly wrap our heads around the usefulness? How can diagrams be a useful tool at all, given that every knot probably has infinitely many different diagrams that could represent it? We could make infinitely complicated diagrams of any knot that we want to. So how can we get any value out of studying the diagrams for knots? That's the big question.